Okay. He was removed randomly. Okay. And here. Okay. So let's see what we have here. Group 12. Uh, Sign groups. Two. Everything. Okay, what did they say I should Humanoid robot learn how to ride scooter. And they turn. That's the title. Ooh. But they have like old pictures. Yeah. Just waste it. That's like very old pictures. Yeah. Okay. Like they say, no publicity is bad publicity. Okay, so I need to go and go. Okay, good. So, welcome to our foreign student friends from Germany, Westphalia University. I hope you can hear me. Can you hear me? I don't have any sound. Here we need to turn on. So, can you hear me now? Yeah, okay. Then everybody in here in the classroom, you have to mute your sound, otherwise we'll get feedback. Okay, good. So, welcome to the class, our global virtual classroom experiment in intelligent humanoid robotics. We've done it several times before, but not with such an ambitious project as what we're trying to do today, or this class, which is to build a rock climbing humanoid robot for the second assignment. So let's see if I missed anybody. So now for the German students, you usually use big blue button, I assume. So I don't know if there is a proxy for that, or if you're already all on Discord now. But we here in Taiwan, we use Discord. And the audio is working. Okay, good. Then, before we start talking about the Mujoko simulator and PID control, we're going to try and talk about the teams. Now, I believe you guys are already organized into teams. Is that right for Australia students?
Yes, they are to some extent. Morning, everyone. Had some issues with the Discord. Jackie, are we recording? Huh. Still have problems with the audio.
Yeah, we are recording here now, and you can start the recording too on your side. David, that's really important now that we get the recordings of that machine posted to YouTube. We must, the recordings from the lectures, we must post them on YouTube. So they're all this week will be fine, but I think in the first time we didn't have any audio. Yes. But now is it fixed? Yeah. Yeah. I checked on it last week. But last week, only right. Yeah. Still for the afternoon. Otherwise, they have all the okay. I cannot hear anything from Australia.
Don't hear me now? Crap.
Okay, so I actually just type. So we have group channels in this Discord server, group 1 to 20 or something. Those are actually just out of convenience. If you want to use those, you can. But you can also use other methods like Telegram or your own server. So, and actually, I probably would like to get rid of those groups because they have to be open by default, and then sometimes we have problems with spam. That would be the only problem. Otherwise, I don't mind running them. So we'll see how that goes. So now, before we start, I would like to assign the groups. So let's try it this way. Who is in group 1? For, let's see, 511. Adri, Nathaniel will join group 1. Then David, group 2. New Joanna 7. Helsinki 8. Much easier. Road 9. Okay, so that's what we have so far. Okay. They can't hear anything. I cannot hear anything from you guys either. Okay, we're just assigning the groups, so you should be able to hear that. Now I hear Reinhardt. Because it's muted on there. What is it? Net deafened? No. Okay. I can hear that. No, I cannot hear you. Okay, so uh, you guys all have your groups now? The four of you? How about Henry? I can add you. David, you have a group already? The two of you, okay, you have to join the Germans as well. Yeah. So the two of you will join the German groups as well, and the two of you will join the other German group. For assignment number 2. Assignment number 1, you still have to finish on your own.
Yeah. So we have new groups for the next assignment?
Correct. Yeah. We'll just add some more to it. So, what's your Discord ID? Are you logged in now?
Yeah.
You're welcome. Channel. Yeah. Okay. Yes. Perfect.
Because my laptop.
Oh, you're already in the episode. This one. Probably. Now you're also in robotics. Then you can join it, and you will be group number. Short intro to Discord. Not sure what intro to Discord you need. Type in the message field. And, wait. Group 9. No, you will be group 10. Okay. You should know your name. There's no mark on here.
Du musst das reinmachen. In eine spezielle Gruppe oder Mark with C.
Mark F.
Mark with a C.
Mark with a C.
Yes.
Mark Schröder, okay. I'm not sure if, how come you're not there?
Yeah, I'm in the intelligent humanoid robotics server now.
You are?
Yeah, the whole time.
Okay.
Who is Reinhard?
Reinhard is the professor in Germany. Oh. And yeah, you're intelligent humanoid robotics, so that will be Mark
collaboration.
Schröder and at
George. So we have to. We also both have to get added to group.
Group 11. The two of you, group 11.
Okay. Thank you. No. We also we're the group, right?
Not 11. No. You are. What's your ID?
My name is Kenneth. I'll be Kenneth. That is no, mine is Sidon. S-I-D-O-N. That one.
So what did I say? Group 12.
Okay.
Capital class, really? Okay, I'm going to. Okay, but what will I get him now?
Can he join group 3?
No.
Okay. Just putting another
Group, he will be. Yeah, but I need his. He's not even connected.
He's not even.
J.
Yeah, oh.
13. We have 13.
Who is our crew?
You should be 12. So maybe. For the Australia students.
12 students?
Like this, we are doing like we are right now. We have a call. With the university group. So we're doing a project signing up to. We actually not just us two, we have two other
Well, I have to go back to the grade as well.
And you? Do you have
Good,
a
good.
already?
That's excellent.
Which one? Six. Okay. So try and join the group channels here and post a message with your IDs so that you can join them. So group 12, okay? Yeah. Group 12 did it perfectly. Group 8, Vince.
So this is your friend. They are
I don't know.
Ray.
There are a lot of
David. Okay, David, you already have your group 2. Already have some messages. Yeah. Okay, good. So then today, after the group assignment, I want to talk about the Mujico simulator and implement a simple system for the simulator. And you should try and work on that with your German students. Mujico multiple objects, joints with contacts.
I just take classes just about this, but only
Multi-giant dynamics with contacts is the name. Google DeepMind developed the new Mujico simulator. It's an open source simulator that does a good job modeling the dynamics of a system, and it also has support for rendering and simulation on the GPU, so it's quite efficient on a modern workstation if you have a dedicated graphics card. Let me just check the groups. Almost. Multiple groups. Okay, Okay, so today we want to develop a simple system with a BID control, and you can do that as an exercise with your colleagues from Australia. And let's base it on the first assignment. So we want to have a joint here. Kind of like an ankle and the knee joint, and then a hip joint. And then on top here we have a rail with a ball, and we want to balance that ball in the center. So this is basically what you need to do with the real robot for the first assignment, right? So let's see how we can simulate this in Mojoko. And actually, the specifications nowadays, a lot of the setup of the simulation is done using USD files, and there's like this OpenUSD project which allows you to not easily, but more easily than having to redesign it from scratch, to move from Mojoko to another kind of simulation environment. Um, the other ones that are popular nowadays are Isaac Sim and Isaac Lab, which is what we're using a lot in our lab. The disadvantage of those is that it's not open source, and you need to have an NVIDIA graphics card. And for the latest version, you need to have a powerful RTX card in order to be able to run the Isaac Lab stuff. So Mojoko is quite a bit easier to install. Another option that you may have heard of that's been popular, especially because it was the simulator that came from Ross, with the Ross built-in binding, was Gazebo and Gazebo Ignition. That development, that one is also open source, but that development has not been very fast in recent years. So it's been kind of stagnant. And I don't think there's any particular reason for using Gazebo anymore. And NVIDIA just announced their latest physics engine. So there's a lot of interest now in, because we had huge improvements in AI in recent years, there's been kind of this hope that this would easily carry over to robotics, so that we would have super smart, super intelligent robots that can help people in the kitchen or do any kind of job that you want to do, or in factories. And you could just tell them to clean up and stack all the chairs over there, and then the robot would be able to figure out what to do and how to do that. That kind of hope has been misplaced so far. One big reason for that is the fact that AI systems working in the virtual world and robot systems working in the real world are fundamentally face different issues. The most obvious one is that it's easy to run a, there's many of them. The most important one, I guess, is just the amount of safety margin you must have. If you have real robots in the world, then you cannot just say, oh, well, if it crashes your car and kills everybody inside, then just reset it, it'll be fine, right? You can do that with a generative AI program. If you don't like the picture, you can click again and generate a different image, or you can change the prompt. But robot systems in the wild have to be a lot more stable and a lot safer. There's also a lot of issues with the training data. We can get curated data sets of millions of pictures of cats and dogs, but what a successful loading of a dishwasher would look like from a humanoid robot point of view is much harder to generate like the training data that we need from the real world. Also, we cannot test out things thousands of times until we find a solution. Your robot will take way too long, or the hardware will be broken already. So at the moment, a lot of it is focusing, a lot of the research is focusing on using some kind of simulation and then training the robot or developing controllers or algorithms for dealing with the task, with solving the task in the simulated world, and then to move it to the real world. But that problem is very difficult because I always say that if you can simulate all the important parts of a particular task, for example, balancing the scooter with the humanoid robot, if you know all the parts of this that are important, and you know all the values that you need to introduce into your model, that the simulation is accurate with matches the real world, then you already solved the problem. Basically, that's just as difficult as making the scooter driven by a humanoid robot, making the humanoid robot balance the scooter. So you want to have a simpler world. Necessarily, your simulation is going to be a simpler world, and you hope they'll be able to bring the knowledge that you learn in your simulation over into the real world, and to bridge this simulation to real world gap is one of the important topics in robotics research, and especially in the context of reinforcement learning. So many teams, many people are working on sim to real transfer and different approaches for trying to do that. AI also has great potential and is used widely now with large language models and visual language models for the higher level interaction between humans and robots, or the higher level task planning for a humanoid robot. But the actual task, like balancing a scooter, that's very difficult. Or in our case, rock climbing robots, the reinforcement learning sim to real transfer approach works well for domains or tasks where the time horizon is quite short. So the robot can learn how to kick a ball, like a standardized motion sequence that is not very long. And that is possible, but rock climbing is much more challenging because you need to not only reason about the individual motions that get you from your current hold, footholds and handholds, to the new place that you want to reach, but you also need to reason about, okay, now if I'm here, then where else can I move? So it's kind of like a path planning, motion planning problem in a very dynamic domain. So modeling all of this would be very good. So we will in this course at the simple version of that, and it's an extension of work that we did previously. Oops. 17G is group 4 Taiwan. Why? Okay. Okay, so they have too many students from Germany. Okay. Okay. We have one more student. Oh, not here. And my view, yes. Okay. There. Um, so the scenario that we have in mind is a much simpler rock climbing scenario, something like that, where we have 3 different types of holes. But we'll build this in a real wall here in Taiwan, and students are building the humanoid robots to do this. But we have 3 types of holes. One is a central one, which can grab either right or left. One is this blue one here, slanted, such a way that I can easily hold it this way, but I cannot hold it if my center of mass is pulling the other direction. And so we have a center one that goes either direction. We have a left one and a right one. So only these 3 types of holes. There's no underhands or dyno moves or anything like that. If you are into rock climbing, you can do that as an extension for the assignment. Then you can pick up your PhD right away after that. And not just from here, you can get one from MIT if you can do this. Like, I'm pretty sure if you can build a robot that can do this, then we're finished. We can all retire. No, if you can plan through this with your robot and MIT is going to give you a PhD and they're going to shut down the robotics department. There's nothing left to do anymore. See how she's. So we started a little bit gentler with just 3 different holes, and the foot can be placed on any of the holes. That's kind of the rules. Okay. So today, first, for the assignment, I do believe in theory, if you have experience with Isaac Lab or Gazebo, let me just post the links for people that are interested. I think the latest version is Ignition. Then you can use that software. But I like Mujoko, so I'm going to use that for the course. And you can kind of see the issue with the rock climbing robots here, the bear simulation, the simulated bear that I have. It needs to figure out where to put the hands and the feet and how to get it up to there. So from this position here, he could probably reach there, but then it wouldn't be able to get up there to the top. So let's see. Now Mojoko actually has a good set of tutorials that you can access from the GitHub. And if you can download the latest release 3.36 from the GitHub repository, which has versions for Linux, Mac OS, and Windows. And then you can uncompress the zip file, and it's a portable app, so you can just put it on any directory that you want. And here's Mujoko 3.3.6. Then you can click on simulate. You can click on bin for Windows. The other ones will look slightly different. and then simulate, and that will open the Mujoko simulator window, um, where you can make Mujoko models, XML files to put it all together or simulate different environments. You can then open your model catalog, and there's a bunch of them that are kind of fun. So cards, I like the cards one. You can just drop a pack of cards onto an object. It can also tell you how fast your system is running at that point. And also we have a humanoid robot model, which is here. Well, doesn't do anything because it doesn't have any controllers yet. It just falls over. Or if you want to, you can have 100 humanoids. Then they kind of all do that. So you can have armies of humanoid robots in your simulation. And if you program them correctly, they will do something useful. Here we have, this is the same. Oh no, this is one humanoid robot with a whole bunch of stuff dropped on them. These are more tests for how fast the simulator runs. Here's going to okay, but we don't want to start with something as complex as a humanoid robot. That's just to make sure that your installation actually works. You should be able to drag and drop the XML files that describe your system. Also, you can define different parts here of your simulation environment and how it runs. This can impact the accuracy and reliability of your simulation. So for the physics, it asks for different integrators. Now Euler integration is the simplest one. Rangekata 4 would be better. We can then load a different model and see if it actually makes a difference. Let's see. Looks pretty much the same. Let's see. Right. So today I'm going to follow a simple Mujoko. Oh, here are the ones that they have in the built-in tutorial. So if you want to learn about the basics, we can have a look at those. I don't think I need to run those separately, but actually, let me just run them quickly. there's a bunch of includes that are included with the Mujuko package, and there's some trickery to get it working on the Jupyter notebooks with the correct library for NVIDIA setup. And then this starts very simple by defining a Mujuko simulated world with two objects in it, one box and one green sphere, and the colors of it, and you can load that. And it tells you a little bit more about it, default objects and things like that. So here it gives you the number of geometries in your object, two, their colors. So we can ask for the green sphere and all the data that is associated with it. And it's RGBA data, which is the same as the color model before. And to get an ID of an object from the name. So Mujoko.geom or model.geom tells you about the geometry of the system that we have. And the different parts that we have for that particular model. The actual state of that geom is then encoded in the MJ data structure, which is what's being populated. First, it's going to be initialized by your reset function, and then it's going to be updated by the simulator. Mujoko, when it runs, it's going to change the values in the Mujoko data structure. Whereas the geometry wouldn't change. Like the sphere, if you generate that sphere, it's going to be that sphere. It won't change to anything else. And then we can, for example, get the position of the green sphere or its velocity. And we can generate a video. Now we have our world. Add some lights to it. Now we can simulate it, but nothing is actually happening yet. So now if we add a join to it, which is the one that actually connects, links geomes together, using a degree of freedom, then we can do a simulation like that. And then yeah, it's a simulation, so we can change gravity and we can make it flip the other way. So now we can have a special kind of shape. Typical, this one dynamically is pretty interesting. Have you actually seen this as a toy before? I think they're also popular in no, that's not it. Fine. Oh, precision metal mushroom spinning top top. I didn't know they have precision for that, and it's sold out. No, none of those. So they kind of look like this, and the since they have video. Yeah. Anyway, I cannot find the video, but basically for that particular toy, it's pretty cool because when when you actually spin it, then not only does it spin like a spinning top, but mushroom spinning top. All kinds of mushroom. This one. No. Anyway, if you spin this, the gyroscopic effect, which is kind of 90 degrees offset of the force that is happening, it'll actually spin on the top. So it'll end up rotating on this small part here. So it looks really cool. This also happens in practice. It's a well-known toy. And here they say they're changing it to Rangekata fourth order integrator, which is more robust and more accurate than just the Euler integrator is. have it spinning there, and then as it speeds up, it actually does that. That toy does this in reality. So it's pretty cool. Starts out spinning on the top, then it drops down, and then it ends up going on the top. So here we can see how the stem changes. Here's another example of a ionic pendulum. Then yeah, this does all kinds of ionic movements. But again, it's a simulation. So here you can look at some of the pitfalls of trying to simulate physical systems. One of them is that unless you do it correctly, you get a systematic error which increases the energy in the system. For example, a pendulum, just a single pendulum, like that. If I hold it on an end and then I let go, it should start swinging, right? Now, here, at the point where it turned around, it is at rest, right? Which means that it doesn't move. At this point here, it would move, it would be its fastest movement that it's doing, right? It's swinging, so it's been going accelerating all the way. Now, it's fighting against gravity, so the velocity is going to go down. So this kind of system will convert potential energy which would be the energy that we get by moving a mass in a field, in a gravity field. Right? If you lift things up, this pen here, if I now lift it up, it has more potential energy than before, right? And if I let it drop, then it's going to accelerate due to that potential energy. Now for a pendulum, it has potential energy, which is this one here. It also has kinetic energy due to the velocity at which it's moving, right? Now, in a closed system, that energy is going to be, or should be, constant, right? If this swings in a vacuum, then it should swing forever and the energy in the system should remain constant. And physically that's definitely true. If you put a pendulum, I'm sure they have pendulums out in the space station and that can swing. Actually, I'm not sure about the space station. Anywhere where we have, on the moon or something in vacuum, that would swing for a very long time. The energy is supposed to be constant, so here the potential energy is converted into kinetic energy, is converted into potential energy again. And then the whole dance continues. So the energy in the system should remain constant. But if you are not careful, or if you use an integrator that has time steps that are off, or the velocity and acceleration updates are not applied in the right order, then you end up with a system where the energy, as you can see here, it should be flat, right? It should be always the same energy. But here, for this one 10 millisecond time step, our energy, the energy of the system fluctuates a lot. So this is not physically very realistic. This will not happen in the real world. So whatever motion we calculate will be wrong. May still be useful for your real robot, assuming that your control algorithms are robust enough, but it's not an accurate representation of what happens with the simulation. But of course, looking at the timestamps here, the more often you do your update, the more accurate your simulation usually is. But it also runs a lot slower. So running from 2 milliseconds or 10 milliseconds to 0.1 milliseconds would be a factor of 100. So there, your simulation would be 100 times slower than if you run it at 10 milliseconds. So there are trade-offs. Even a simple thing like a single pendulum like this is hard to simulate accurately without messing up the energies. And then if you increase the time step, you can see the energy then completely blows out of balance here. So now I want you to, as the first step, actually, I think we talk about adding the joint first. Now, that means it's not constrained, the joint. It'll just move the box to wherever we want it to go. And then it's just going to drop onto the floor. With the contact, we also visualize the forces that are acting on the vertices of that particular box. And then friction. So first, as your group, you can work together. First exercise. Build a simple 2D leg in Mujoko. Based on the tutorial, so the leg should look like this. And so we have three one, two, three, four geoms, 5 for the foot plate. I'm not sure if we need the foot plate or not, but you can add one here. Okay. Let's say these ones here are one unit by 4 units. The servo motors here, 1 unit by 4 units. This one, let's make it 5 units and 0.1 units high. And this one here, 5 units and 1 unit high. But you can use any other dimensions that you want, but those are the ones I'm going to use. Okay, so create a Mujoko XML file based on the tutorial. And we also want to have a ball. Let's do the ball here. So you can work together in your groups. So basically it'll look something like that after you're done. The leg should, depending on how you set the initial condition, the leg should just collapse or swing around like that. So now let me think how I'm going to, I want to check if I have NVIDIA support. So I'm just creating, I guess, let you follow along on, if you use Windows, you can. Yeah, I need to switch. So create a virtual environment. Actually, I don't think I do Windows. Oh, I do. Okay. Uh, okay. Movie 15 small. Control Pro. So one advantage of Mojoko is that it actually is only 20 megabyte download in size, so it's pretty easy to install. Not a big download. Okay, then let me see if my installation was correct. Let's try. How do I do that in Windows? No. Dollar environment. Colon. Go. GL. I was using it before. So I don't think I can get the the GPU to work. Okay, I just try this. open the shell. It should work. At least I'm in the right virtual environment. So let's just call that test one. And now I want to build my leg. So let's say that would be the calf. And later on we're going to use right and left. But it's probably a reasonably good um, policy to try and come up with a system with how you name things, especially with humanoid robots, where we have many degrees of freedom. So for one thing, I usually either have .l and .r for left and right leg, or left and right calf, or underscore. So let's see if in Blender I usually use dot. So let's see if that is accepted. I'm not sure. So here would be the first thing we want to generate is the calf and the thigh. And we make it different colors. So let's make the calf a box. And I said 4 and 1. So don't want to make it too big. So 4 centimeters, 0.01, 0.04. And the depth I didn't specify. You have the servo motor here. Let me just have a look at it and guess what the correct size is. Yeah. So if you look at it, then this is the leg that we built. One of the students built for the course and the thing. So this is what the servo motor looks like. So I just want to model this one now, approximately using the Mujoko simulator. If you want to, you can make it more accurate later on. But I think 1 and 4 is kind of correct, and probably also 4. So we'll go with 1, 4, and 4 centimeters. Actually, before I cut those in, I just want to visualize it. I want to make sure that it actually works. Here's our model.
Yes.
First, we have to import Mojo.
Mm.
He had renders it, but renders it as a HTML object. So on that code, if I want to actually show it, and then
My friend is currently not on the meeting, so he want, can you join my group?
no, he should join another group. He was supposed to be here at the beginning, so we may have to reshuffle the groups. So what's his ID?
4117, the whole 26.
Okay, so we have two more students. Okay, yeah, he will have to wait. 4117. 4117. Okay.
Close everything.
Oh, show image. Okay, we can try that. This is just a Chinese version. Let's see what ChatGPT. OMG viewer. Surely no Python either. A lot of. Okay, I should have just gone to the Moodle code GitHub instead of using ChatGPT. Yes, one other reason, by the way, that why I chose Moodle is that you can actually compile it for WebAssembly at the moment. So you can actually run the full Mojoko simulator in your web browser. So here I don't need to install anything. It just runs in the Edge browser, which is kind of cool. That's the media file. That's far. I think I have to convert to display it using numpy maybe. Oh, renderer the render. Okay, render dot render. See how that works. Okay, then it's happy with that, and I don't use media file or media file. So we'll import matplotlib.
Ja. Hallo.
I am show, not show.
Nee, ich bin gar Sie sind im Haus, ich komme vorbei.
ELT dot show. Okay, now we have an image, but all black, so we're looking at the wrong place. I think. Let's see what I use the original. Okay. So now let's try and build the body here. Put the light a bit higher because we can build a larger humanoid. So the view of the camera to oh, 0.04. And maybe I make it 0.5. So that looks better. And I'm going to need to change the viewpoint. And if I try, maybe I'll go. Do I have Jupiter? So I don't want to run this in the Jupyter notebook. I want to be able to run the code directly as a Python module. So that's why this doesn't work. So let's try 3 joins, calf, thigh, and hip. Now I need to set the position. So let's put this position as 0.00, 0.00, and the size. And here our position then for the thigh, that will be the center. So actually let me move Z up by half of the width, half of the height of the calf. So that would be 4.5. And now the height here should be zero and high 0.5. And let's make that one green. And then hit. Zero point zero 0.05, 0.10. And let's make this one blue. And let's see what we get. So if I change the top one to 0.1, just so that I get my orientation right. Okay. Of the and here I want to change the camera and show the world part.
Hmm.
10 meters with one and one. So here's our width. Then I want to change X and Y.
Hmm.
We'll call this the side camera. So that would be looking at it from the left side. The position here. Find out. but it shouldn't be. Unfortunately, I can only get one image. I can't rotate it, so it's hard to guess what image to look at to get the proper side view, which is really like to get. So let's see if now we're up. Okay, so this is a top-down view, I'm pretty sure. So that means X and Y and Z is going upwards. I move the camera to that position, move it to fly. can watch. Okay, so we just need to attach two Taiwanese students to groups. Way has it got to go?
Yeah, so for those Taiwan students, you need to stick with the group, like the ones in house.
The ones that I already announced, you stick with that group. Yes. It's just two extra students that showed up late. You could have 1, 2, 15. Will be attached at the one students. True. And who is running now? And so we added some other students. Group 7. seeing group 7.
I should be at the group one, but there's no one in there. So there's the student who asked me to see the group settings because they're like groups.
No, I mean, why do you think I posted this? Here are the groups that were assigned so far.
Yeah, I just have some misunderstanding, but I already said I have not the group one or another. Yes.
Okay, so you go to your group, the one that I said you would be in.
Not the group one. I already did.
Okay.
There's no other student there.
Okay. German students from group 1 should join. What was your ID? 411. Okay. Okay, so who are those two students that haven't? Well, now there's a whole bunch of other people coming late for the lecture. Okay. Actually, what happens if I unmute you get feedback? Okay, so send me a list of the students of your groups, the groups, so that we can have posted on Discord. Now we have. Okay, good. Then finish working on your Mujoko. Finish setting up the leg of the robot using Mujoko. And you can follow along and let me know when you're finished. and I have the leg. Um, I want to 0.5, 0.5. I just want to generate a nice scene to model that, like a nice picture. So our grid is okay. And 1 meter by 1 meter. No, I don't want to go that far. So here we have lower calf. That would be a view from the top. And it would be so then let's try and see if we get a left view. I don't need to change it all the time. So left view would be 0.x, y, z. Let's try -5. So you have your group. We mean you don't know. I mean, right. But did you get a message about your group? What's your ID? LZ? Okay. So moving on. Then we will have to assign you a group. Anybody else here doesn't have a group yet? What happened to Benson's stuff? You said there was one guy without a group? Benson? Let's have a group 17. That's here. And then let's see. Put it out. Yeah, the problem is because we only have 13, and then we merge groups together. So, which group are you two? Two from Australia already? The two of you?
Group 11.
Yeah. And you have contacted them?
No.
No? Okay. Contact them now, and you guys?
Group 12.
Group 12? Have you contacted them?
Yes.
Okay. And they said hi?
Yeah.
One of them is.
Okay, good. Then at least group 11 is done. If you have not managed to contact your counterparts, then let me know now. You?
Yes, my teammate jumped to
And there's both German students. I don't know if they are offline or there's one student.
So who jumped to group 7 then all of a sudden? The whole point why I assign groups is that you cannot just jump groups.
The German student Michael. Initially he's at 26, but then I see that he's also there. What vessel and the others.
Okay. Um, and you have not contacted anyone of the German team.
Yeah, there's a lot of time at
Okay. Then let's see what we have for group 1. Group 1, can you join the group 7 with us so we get 4 members of the team? Only, most groups will only have one Taiwanese student, I think, at the moment. So don't join for 4 group members or anything like that. Stay with the group that you were assigned. Group 4. So I will just go through with the groups that have already responded. And then we can.
Hello, Professor. Hello.
And who is this? Tai Hao. Yes, from group. All right, so until next week, stay with the group that you were assigned to. Today, may need to do some reshuffle next Monday. Taiwan. Okay, so group 8 looks good. Because we have 13. Okay, there's also some German students that don't have a group yet. And some German students that haven't corresponded with their Taiwanese students yet, and vice versa. Okay, so now I have one, and that would be Todd. The size is half of it. And I want to bring the camera back a little bit. Now our top plate. Now I want 0.01 instead. Zero point 0.2. And now it's dark because the light is coming from the top. So I have to put on another light. So I should be able to generate two views. And one set this off. So here we have the top view and that should be here's the leg, the left view, and the top view. How deep did I make the top? And so that here, that's yeah, that would be 0.04, 50 centimeters by 50 centimeters, too big in practice. So then here we have our hip top. This is the leg from the side. That part here is missing one thing because of the shadow. Should be the right part. So if I bring it at 2.5, then it should. Okay. Okay, so we have three. We will assign them on next Monday. Yes, we'll check next week. So 3 Taiwanese students we will assign next week. Okay, good. And that's it for today. So work through your Mojoko tutorial. Make sure you can actually build a lake like that. Then next, until next class, you can add the joints so that you can actually make the lake move in the simulation. So that's just
Mr. Walters, are we going to have a midterm exam?